Anyways,
Yeah.
that went in the recording. But anyways, hello everyone. I am super excited for this class and to introduce the person who is taking this class. It's Sanjana. Sanjana, if you all probably know about her already, but she has represented India at the European Girls Math Olympiad twice and got us a bronze and a silver, very yours. And she is also the director of Online Math Club. So cool. Uh, and yes, she has qualified for the IMOTC 3 times, and she has also done some cool stuff that I got to know today when I was going to introduce her. Is it okay if I mention that? Or
Sure.
okay, she has also written a book that you can look up in 2020, and she's also very good at French. And also, yeah, I think that's most of it.
What is the book called? Geometry, algebra, what?
No, it's fiction.
Yes. Okay, over to you,
Okay.
Sanjay.
Is it called The Strength of a Bond? I just
Yeah, it's that. Okay, let's start. Okay, so I hope you can see the screen. So today I'll be having a problem solving session on geometry. So these are just some extra problems which you can try in case you are done with the problem I'm doing or if you have seen it before. So if you want, you can take a screenshot right now and then I'll start doing the problems. So, okay. So I have some problems, around 6 problems, and I'll be starting with some fairly easy ones and slowly increasing the difficulty. So for each problem, I'll give you a few minutes to try, and if anyone has any ideas, please feel free to speak up. It doesn't matter if it's correct or not. And I'll eventually give hints and then get to the solution for each problem. So this is the first problem. I'll draw the diagram and you can try it for a few minutes. So you're given a triangle ABC and some length conditions. So you have D such that BC is equal to CD and D is on line BC. And you're also given E on line AC such that AE is equal to twice of CA. So this is equal to twice of this length. And you're given that AD is equal to BE. And you're supposed to prove that ABC is right angled. And right now you're not given which vertex it's supposed to be right angled at, so that's something you'll have to figure out. So yeah, you can try this, and if some people have seen this before, then you can try the extra problems.
just want to be clear about the first extra problem that you've given.
Okay.
So in that extra problem, they said, suppose the internal and external bisectors of angle BAC intersect BC and omega again at K and L.
Yeah, so the internal bisector intersects at BC and the external bisector intersects the circle.
Okay, cool. Thank you.
Okay, sure.
Wait, could you show the extra problems again?
Okay.
Got it, thank you.
Sure.
Just looking at a diagram, A seems to be 90 degrees. Just looking at it.
Yeah, that makes sense.
So I tried for assuming A is 90 and it works out pretty nicely. So I think by making some sort of phantom pointy thingy, because then we can say if A is slightly greater than 90, then this angle is going to be, this length is going to be larger, or vice versa. I don't know which yet.
Okay, what
But-
is your argument assuming A is 90?
First, it just looked 90, so I tried 90, A is equal to 90. Okay, the lengths work out perfectly. It's same. The height is the same and the base is the same, so it's the same. Then what we have is if A is less than 90, maybe I can show that one AD is greater than BE or something like that. Not that direction necessarily, but something along those
Okay.
lines.
Yeah, that could work. You can try more and let us know if you get something.
I'm not sure if this construction works, but maybe because everything's getting like reflected along a point, so we can reflect A along point C to A dash
Okay.
perhaps.
Okay. So you get a parallelogram.
Yes, and then AD moves to BC. AD and B A dash are equal. So we have an
Yeah,
isosceles triangle as well with A dash BC.
that is true. So you have some angles equal here.
Oh wait, then we are done, right? Because it's an isosceles triangle and AC is equal to AA dash.
AC is equal to AA dash.
Because AC
Yeah,
is
okay.
A is twice AC and AA dash is also twice AC.
Wait.
That's
Okay,
E.
yes.
That's E. AE
Sorry.
is
Yeah, this
A.
is
Oh yeah, I can't see the bottom, so sorry.
okay.
I think I have separate solution.
Sure, go ahead.
Like A is the centroid of triangle EBD.
Yes, that is true because you have that EC is the median in this triangle and A divides it in the ratio 2:1. Yeah,
And
so
then-
go on.
And then extending DA to meet EB,
Mhm.
we get that at X, say, then AX is AD by 2,
Yes,
and that is EB by 2.
yes.
We're done.
So yeah, basically this length is equal to this length and all these three are equal, right? So that means that X is the center of triangle EAB, which means this angle is 90 degrees. So I'll just go over what we did once more. So we noticed that A is dividing this line in the ratio 2:1. So, and we also have that C is the midpoint of BD. So that ideally would remind us of a centroid because a centroid divides the medians in the ratio 2:1. So now you try to use the centroid condition again. So if you consider the median DA and extend it to X, you have this length condition. So AX would be half of AD, but that's also true that EX and EB are half of that length because you're given that EB is equal to AD. So then you just get these equal lengths and it's easy to show that this angle must be 90. So that's how you motivate this. If anyone has any questions, please feel free to ask at any point.
So would my method work, like the reflection of A along C?
I'm not sure. So
Because if we use, I think I finished it also because
okay,
it becomes
Yeah.
like A dash BE is an isosceles triangle.
yeah,
So and A is the midpoint of A dash E.
yes.
So we are done.
Oh, okay, yes, that also works, correct. Yeah, so that's also a useful thing to note because you have a midpoint and you have some equal length. So this gives you a very nice parallelogram. So you can finish using angles. Okay, nice. So that was one of the warm-up problems. Let's move on to the next one. So you have triangle ABC. again. M is the midpoint of BC. And okay. You have the foot from C to AM. You're given that the circumcircle intersects BC again at Q, and N is the midpoint of AQ. And you want to prove that NB is equal to MC. So essentially that N lies on the perpendicular bisector of BC. So that would also mean NM perpendicular to BC.
First, I think we can project the A onto BC.
Yes, that's a very good idea because you get
Because then
another, yeah, cyclic quadrilateral. Okay, so let's call this D.
so we want to prove TM equals to MQ.
Yes, because then you just have midpoint theorem.
Is it just me or what we're trying to prove looks somewhat like the butterfly lemma?
What is the butterfly lemma?
Okay, butterfly lemma is you're given a circle and a chord, and you're given the midpoint of the chord, and then you're given that you're given two chords passing through M, and they intersect here, and these two are equal if M is the midpoint of the initial chord. And yeah, it kind of looks like that because you want M to be the midpoint of two things.
How do you prove this lemma?
Cross
It's
ratios work.
yeah, projective cross ratios.
Oh,
But yeah, it looks like that. I'm not sure if we can apply that here, but there is an elementary approach to this, so you could try to find that.
so we have so if we only consider the red circle, we can
Okay.
basically assume that B is out of the picture, right? So we can just have M is any point, right?
Mm,
And we have AC as a circumcircle. So basically we have any point, AC is a circumcircle, and no, we still have a black point defining that thing.
yeah, you still have the midpoint condition.
I think I got it. We can do power of radical axis on the red and the blue circle.
Mhm.
So like
Yes.
we get that MD times MC is equal to MB times MQ. Which one
Yeah.
is
So you have MD times MC. Now, if you look at the red circle, it's equal to MA times MP. But if you look at this black circle, you get MD times MQ, MB times MQ.
yeah.
But yeah, MC and MB are equal, so
Oh, and
you
now we're
just
done.
get, yeah, you're done. Okay, so what happened here was we initially introduced the point D because then we get a really nice cyclic quadrilateral. And now we reduce it to proving that this is 90. So you want M to be this midpoint. And now since you have two intersecting circles, you have the common chord and you have some other chords, it's natural to try to use power of a point, and that just gives you the conclusion. Okay. So now let's move on to some slightly harder problems. And okay, before we try this problem, I just want to prove another lemma which would be useful here. So if you have a circle and you have a chord and you have the midpoint of this arc, then if you have these points and this is the midpoint of arc, you have MA squared is equal to MB times MD. And you can just prove this because of the angles. So these angles are all equal because it's the midpoint of arc. And so you get this power of a point relation because of the similar triangles. So what else you can do in such a scenario is you could introduce another chord like this. So say this is X and Y. And so you get that this is also equal to MX times MY. And these would be cyclic. So that's in general a useful relation to have when you have some midpoint of arc. And that's something to keep in mind.
How is MA times MB equal to MB times MD equal to MX dot MY?
Oh, because you can use the same logic, like this is also equal to MA squared
How
by
do
the
you prove this
same
is
angle.
equal to
Oh,
how do you prove
similar
this?
triangle. So you have MAB is similar to MDA. Do you see why?
Uh, yes.
Yeah. So yeah, I hope this is clear. If anyone has any questions, please ask. So, okay. This was just to sort of help for the problem I'm going to do. So you're given, again, triangle ABC. And yeah, I'll draw the diagram. Okay, so you're given triangle ABC and you are given a point D on BC such that the angle formed by DAC is the same as the B angle. And you're also given a point X on ABC such that AXI is tangent to AC and it's passing through I. So basically that just means angle AXI is equal to A by 2. So now you want to prove that the angle bisectors of CXB and DAB intersect on line BC. So you want to prove they intersect at this point D. And yeah, so obviously XT would also pass through the midpoint of
Why is
arc over
angle
here.
EXI A/2?
Because AXI is tangent to AC. So this angle is A/2. So that would be this angle. That's just the condition
Oh,
equivalent for
yeah.
X.
got it.
Is the converse of the statement you just proved also of the lemma also true? Is the converse of the lemma also true?
By converse, what would you mean? Like,
But I mean that if we have a circle and
Mhm.
we have a point M, A, and D,
okay.
then if M the point, if MD times MB is equal to MA square, then the line passing through AD intersects at C. If the line passing through AD intersects the circle at C, then M is the midpoint of RKC.
I think that should be true. I think you can just introduce a phantom point and prove that it has to be true.
Okay, one thing we can see is that the circle ADB should also be tangent to AC at A, if I'm not wrong.
Wait,
Because
which circle? Because
ADB.
AXI is different from ABD.
Yeah,
Yeah,
but it should also be tangent. So I think
yes.
those two circles are homothetic then.
Yeah, that makes sense because they're tangent to the same line at the same
Yeah.
point. So those two circles would be homothetic.
Which two circles?
AXI and ABD because so AXI is tangent to AC at A. We know that, we're given that. And ABD is also tangent at A because you have both of these angles are B. Like DAC and DBA are both B. So that's also tangent. So if you have a line and two circles are tangent to it at that point, they must be homothetic. That is a good observation.
Yes.
Angle is a angle AXI equal to angle MXC and angle MXB.
Yeah, that should be true because all those angles are A/2.
Wait, what did he just ask?
What's M?
I think you meant this one, yeah.
What did he just ask? I didn't get it.
So MXB and MXC, both of them are A/2 because M is the midpoint of this arc. And that is equal to AXI. That's what he just said.
XM is the angle bisector of angle CXB.
Yes, because the angle bisector must pass through this midpoint of arc. So we're just defining it as that.
How about we extend AD to meet the circumcircle somewhere, and then at least that will make BC also an angle bisector, because
Okay.
proving three angle bisectors concurrent seems nicer.
So you're saying we introduce some point here?
Yes, and join that to D, and join that to B.
Sure. Okay. Yes, so we would get another angle bisector here.
So then T would have to be the in circle, right? Of this
Yes.
ABD prime.
That is
Instead.
true.
So it's done.
How?
Yeah.
How are we
we're
done?
done.
Because
How?
it's the angle bisector 80.
Okay, yes. This is a much shorter solution than the one I had in mind, but
We're done.
yeah, we're done.
How we?
Because wait, are we defining things correctly? Because
We're defining T as the incenter of AB D prime, but we're yet to show that like
yes, it should lie on CXP. Yeah, sorry. Yeah.
I didn't get how is T the incenter of AB D dash?
Okay, so we define T as the intersection of the angle bisector of ABD with BC. And now what Shreya said is we extend AD to meet the circumcircle at D dash. So then we already have that this angle DAC is B, right? So then the angle D prime BC must also be B. This angle and this angle.
Oh, yes, yes.
So yeah, we have two angle bisectors, so it has to be the incenter. Now can we use this?
So let us,
Yeah,
why
go
don't
ahead.
we just make a perpendicular on is from AC on A? I think we should do that.
We have to show that D dash is M, right? Then
No, no. We have to show that XT is T. We have to show XTM collinear. Basically, we don't know that yet.
or we can alternatively show that BX by XC is BT by TC.
Yeah, that's also true.
Bx by xc is equal to what?
BT by TC. That's just the angle bisector theorem. Like, if you have an angle bisector, say,
Oh,
yeah,
yes, yes.
okay.
Uh,
Also, something else you can notice is we have one ratio condition you can use, the angle bisector theorem, and you have a lot of angle bisectors. And you also have similar triangles because of this D point. So in general, you have a lot of ratios. So maybe you can play around with them and get something nice.
how do you make a circle tangent to a certain line passing through a certain point? How do you construct that?
Okay, so you would want it to be the center to lie on this. So, okay, you want it passing through A and I and tangent to this line. So you'd want this to be perpendicular, and you could just take the perpendicular bisector of this, intersect it, and then you'd get the center. Like the center would have to lie on both these lines.
Yes. Can you make uh can you make the perpendicular on A from AC onto on A?
Okay. That would look slightly weird, but sure. Okay.
Doesn't it also suffice to prove that MT into MX is equal to MB squared?
MT into MX is equal to,
Yeah, because of the
yeah,
lambda that you did.
yeah, that would suffice. Sure. You could also just intersect MT with the circumcircle at X and prove the angle condition about X. That would also work. So then you would directly get the ratios.
I think X is a very weird point. So
Mm,
maybe well,
Yeah, that is true. So X is like some random intersection of MT with the circumcircle. So maybe we can find something nicer about T that could
yeah,
help us work with X better.
yes. What do we know about intersections of two circles?
Radix, but like that isn't very helpful here.
Oh, I know we can make the perpendicular bisector, or no, we can make the point that passes through the centers uh, of the two circles, and A will X will be the reflection about A on that line.
Could you repeat that? Which two circles?
We have only two circles, right? If we make a line that passes through the centers of the two circles, then X will be the reflection about A on that line. By
The
definition,
okay, yeah, the radical axis.
no, not a radical. The same thing that passes through the centers, right? What do we call that?
Okay, you're talking about AXI and ABC.
Yes, the thing that passes through the centers of the circles.
Okay, you're taking. Yeah, sure, that is true. Okay, so I'll just write down some of the ratios that we have and let's see if we can get something. So we know that CAD is equal to CBA, and since both of them have the common angle at C, we get a pair of similar triangles. We get CAD is similar to CBA. And so we have these ratios. So, and we also have a lot of angle bisectors. So maybe try using these ratios in relation to the ratios you get from the angle bisectors.
So how are we like defining X again? By our new definition?
No, yeah, our new definition is X is empty cap the circumcircle. So we want to prove this angle condition about X, like AXI is A by 2. That seems like a more natural thing to work with.
We want to prove XIA is equal to B, right?
Why is that true?
Or is it ulta? Am I saying something?
Wait, are you asking what we want to prove? Or
Yeah, we want to prove that XIA is 180 is B, right? Or am I?
we want to prove AXI is A by 2. Are you saying it's equivalent to XI is B?
Yes, I'm asking that. I think it is.
Okay, let's see. So yeah, okay, let's just call this point, say K. So you know that AXTK is cyclic, right? Because of the thing we did before. So we know
AXDK. How do we
X
know XDK is cyclic? I didn't get that.
because
Of the
MT time,
lemma.
yeah, I'll just write it. MT times MX is equal to MB squared, and it's equal to MK times MA. So we know that it's cyclic, so we know the angle AXT. It should be equal to this angle, which is A by 2 plus B. And we want to prove AXI is A by 2. So we want to prove TXI is B.
Wait, does this not mean you're assuming that T already lies on BC?
No. Yeah, we are taking T as this angle bisector point, and we are defining X as MT
You
cap,
took
the
T to be
circumference.
the angle bisector of which triangle again?
BAD. That's already like there in the
Yeah,
problem.
so then we can't say much about T. Okay.
Like you want to show the angle bisector is concave, but instead you're assuming X lies on MT and you want to prove the initial condition about X. That is equivalent.
Yeah.
Yeah, so now you want to prove that TXI is equal to B.
We also have that the three ratios like CB upon CA is equal to CA upon AD is equal to AB upon AD, AB
Mhm.
upon AD is equal to BT upon TD.
Exactly, yes. And can any of these be equal to something else as well?
CA by CD would be A by IK. No, CA by
Mm,
CK.
Yes, but what would CA by CD, what would CB by CA be equal to by a similar logic?
CB by CA would be AF by FB, I think.
It would be BF by FA, right?
Yeah.
And what does this give you? You have BF by FA is equal to BT by
Sorry, but what
TD.
is F again?
F is just the intersection of the angle bisector with the side. It's here.
So FT is parallel to AD.
And yeah, exactly.
How
So
did we
maybe
get
we
BF
can,
by FA is equal to CB by CA?
because CF is the angle bisector of ACB. And similarly, yeah, did you get it?
Yes.
Okay. So you have that TF is defined as parallel to AD, and you want to show that TXI is equal to B. But now that you have TF parallel to AD, can you say anything else? Like, can you get any nice angles here?
One thing is that AD is like BAD is tangent to AC and FT is parallel to it. So we should get another thing which is, but it's not tangent to AC anymore. It's not as nice.
Okay. And
Angle
okay,
BFT is equal to C.
BFT, why is it equal to
Wait,
C?
I'm not sure. Wait,
It
I
should
might
be,
have made it wrong.
we have BFT equals BAD equals BAD prime equals BC. No, it's different. It equals BCD prime instead.
Yeah, I might have made a mistake.
So
It's
that's a
fine.
difference.
Okay, I'll just mark the parallel things.
Wait, angle BFT is equal to angle BAD, right?
Yeah, so it should be like angle A minus angle B.
Yeah, that's right.
But we're not getting anything about X because X is the weirdest point right now. And we need to get something about X to do anything.
Okay, but we just reduced it to showing TXI is equal to B. And also remember that you have MT times MX is equal to MB squared is equal to MC squared. But what else could MB and MC be equal to, especially in this picture?
MI by insertion.
Exactly.
MI.
Exactly. So if
How do
anyone
we get
is not
that?
that you can angle chase that, it's
Incenter
called
lemma.
incenter-accenter lemma. It's just you just find this angle and both of these angles are equal, so MB is equal to MI. So yeah, if anyone has any confusion about that, then you can ask and I can show you. But Yeah, so we have mt times mx is equal to mi squared. So that means we have mti is similar to mix. So what would txi be?
TIM, I think.
Exactly. So we know TIM is, we want to prove TIM is B. So we have actually completely gotten rid of X.
Can you please explain the eccentric thing a bit?
Okay, sure. So all it's saying is if you have a triangle, then with the you have midpoint of arc and in center. It just says that these three lengths are equal. And if you want to prove that, so you know that this is a by 2. You know that this is b by 2. Right? So you want to show that
It's
b.
A.
Yeah,
Oh,
yeah.
ha, A by 2. Good.
Okay. So you want to show that angle BIM is also equal to a plus b by 2. And you know this is 90 plus c by 2, right? AIB is 90 plus c by 2. So this should be equal to 90 minus c by 2, which is equal to this.
So we know that angle BFT is equal to A minus B, or am I wrong?
BFT is a minus b, that is correct. Also, yeah, because of the parallel lines, you get that this is equal to this angle, like because you have the angle bisector. So you have AF is equal to FT.
So then AFTC should be a kite, I think.
It should. And yeah, can you prove it? Like it's
Because like from the lemma, from what we have that BFT is A minus B, then we have that FTC is just A. And like
yes,
we're done.
yes. Wait, FTC is A
Because it's
because
like B plus A minus B.
yes, exactly. So FTC is A. So we have that like both FAC and FTC are equal. So the entire thing is symmetric because CF is the angle bisector. So we want
Sorry,
to
but I
prove
didn't get your AF equal to FT.
because so we have FT parallel to AD and we have these two are equal because it's the angle bisector. But because of the parallel thing, we have this is equal to this.
Okay, I
FTA
got
is
it.
equal to TAD.
Yes, yes.
Yes. So then we realize that T is just the reflection of A over CF because the whole thing is like completely symmetric by angle chase. And we want to prove this angle is B. But now you know that's true because of the reflection. So we're done. So I'll go over the whole thing once more because this is sort of long. So first we just redefined X because the initial definition, this definition is easier to work with. And then using angle chase, we got rid of X entirely and we reduced it to showing this property about T. And then we used ratios from similar triangles and the angle bisectors to get this parallel condition, which implies that T is the reflection of A over the C bisector. And that just finishes the problem. So does anyone have questions?
I'm sorry, but could you write down the key steps?
Sure, sure. Okay, so first we use angle chase. Yeah, first we used some angle chase to get rid of x, and then we used some ratio chasing to get the parallel condition, and then it's essentially some more angle chasing to show that T and A are reflections, and then it's essentially done. So, okay.
Is
Wait,
there
so
a
did we
neater
need this?
solution?
Hmm?
Is there a neater solution? I mean, it looks bit neat, kind of.
You have another solution?
No, I'm asking, is there a neater solution?
Okay, I think there's another solution which involves some projective things and Pascals, but I wanted
This
to
is
keep
very
this.
neat, I feel. Like, this is a very, very clean solution.
Did we ever
Mhm.
actually use triangle MTI similar to triangle MIX?
Yeah, so we got it to proving that TXI is B, but then we used the similarity to show that it's enough to prove TIM is B.
Okay, so then how do you finish? Like you said, it's a reflection, so
How do you get TXI equals to B again? I mean, how do you prove that it's equivalent to proving TXI equals to B again?
So, okay, you want to prove this angle is B, right?
Yeah, how do we prove that we want to do that? How is it equivalent?
Okay, so that's the same as proving this angle is B. Okay, yeah, I think we still need to angle chase a bit here. Yes, so we know that KAC is, we know that DAC is B, and we want to prove that this is B. And we know that AB TSB. So this is equivalent to proving ABTI cyclic. Yeah, we're still not completely done.
I didn't get you. So how did we prove that if we prove TXI is equal to B, we are done?
Okay, sure. So we want to prove AXI is A by 2. Did you get that? That
AXI is A by yes.
Yes, so that's just the tangency condition. So now you know that AXTK is cyclic. Is that fine? By the lemma we had before. Because
Oh,
of
yes,
this.
yes, yeah.
Yeah.
Mhm.
So you know that AXT is equal to AKC.
AXT is equal to AKC. Yes. No, yes, yes.
Yeah, and AKC is A by 2 plus B. So it suffices to show that TXI is B, because then you'd have AXI has to be A by 2.
Yes.
Okay.
So we aren't done, or
We're almost done. It's just you need to show AITB is cyclic, which is angle chase. Like, okay, you know this angle. You know this is B. Yeah, you know this angle is B. And okay. So you want to show that that's equal to BAM.
Okay, so we want AITB cyclic, right?
Yes, yes.
So then we can say that AIT is twice AI F, I think, right?
AIT is twice AIF. Yes, correct.
And AIF is 180 minus AIC, so we can find AIF and therefore AIT, right?
Yeah,
So
yeah.
we're done.
Yes, so AIF is this angle, which, yeah, it's 180 minus.
It should
Okay,
be
yeah,
90
yeah.
minus C by 2, I think. Not sure. No, that doesn't make sense.
Okay, we have C by 2 here,
180
and we
minus
have
B by 2.
what?
It's 180 minus B by 2, AIF, or am I wrong?
Okay, we know AFC, right? AFC should be 180 minus C by 2 minus A, which should be B plus C by 2. And AFT is twice of this. So it's 2b plus c, which is 180 minus, what is this? This is, okay, let's just say it's 2b plus c. So if AFT is this, then can we find AIT?
Sorry, I'm
Okay, yeah, it
confused.
works. So
Sorry.
AIC is like 90 plus B by 2. So AIF is
Mhm.
90 minus B by 2, then AIT is twice that, so 180 minus B.
Correct.
Okay, yeah, so
So,
you
sorry,
just
I'm
found the sign.
confused. Sorry, I'm confused again. Why is proving AXI equivalent to showing it's a circle? I mean, why are we equal to tangency?
Yes, there is some internet issue, I think. Let's just wait for some time for it to be back.
Can anyone tell me why proving
Oh.
AXI is A by 2 equivalent to showing its tangent?
Because then you just do the angle chase, right? So then you
What
want
angle
to prove
chase?
TIM. Okay, you want to prove TIM is equal to ABT. And if you look at the angle
TIM
diagram,
equals
that's
to,
basically just ABT acyclic.
how do you want to prove that TIM equals to ABT?
Like TIM is B, so is what we want to prove, right?
I am
Because
confused.
because you have MT times MX equals MI square. So TXI is just MIT.
I am confused.
Because you just use alternate segment theorem.
I don't know what that is.
It's the basically the similarity. You have that MTI is similar to MIX because of the length ratio that we have that MT times MX.
No, I got that. I'm saying why. I'm asking something else. I'm saying that why are we done if we do AIX equals to AIX by equals to A by 2?
Because that, okay, so we're defining X phantom point in a phantom point way. Basically, we wanted originally that given AIX equals A by
No,
2, we wanted
I
X
get that you want to
topology.
prove stand. I get that you're trying to prove tangency. But
Sorry?
how does I get that you want to prove tangency. But how does showing AIX equals to A by 2 show tangency?
Because again,
Yes, sir.
right, same thing. Like
What thing?
you just do the alternate segment argument again. The exact same argument. Let xi meet AC at some point, you get similar triangles, blah blah blah.
I don't get you first thing. I don't get you.
I guess someone else can try then. Maybe I'm just missing something. Maybe I'm saying something wrong. I don't know.
Sanjana is back, I think. Or is it the same?
Am I
Your voice is breaking. Yeah, I'm not able to hear properly.
There was some internet problem before.
You're muted, ma'am.
Oh, can you hear better now?
Yes.
Yeah,
Yes.
that's much better.
Okay, okay.
Shreya, do you want to make Sanjana the co-host? Yes, I will do that. And I'll make you co-host.
Okay, so yeah, I'm just
So why are we?
Yeah, you're
last
breaking up still, I think, Sanjana.
more.
Still cannot hear you properly. Can you yeah.
Ma'am, so why are we done if we show that AXI equals to A by 2?
Sure, Stan, wait, let's figure out the
So ma'am, why are we done if we show AXI equals to A by 2? I didn't get that exactly.
Okay, so because we want to change it. See, initially in the problem, we were given xi as tangent to AC. Now we redefined x and we want to show the initial condition is
Yes.
true. It's like
No, I
phantom
get that, but
points.
why does showing AXI equals to A by
Okay.
2 show that it's tangent?
Because IAC is A by 2.
Yes.
So if AXI, you just have like tangent circle. Like if this angle is equal to this angle, that means the circle is tangent. Okay.
How do we
So-
do that? 1 second.
That's just angle chasing, or alternatively, you can look at it as like you can take a cyclic quadrilateral and move two of the edges very close to each other. Then that basically gives you this result.
Oh, I got it.
Okay, sure. So yeah, we reduced it to showing TIMSB, which is equivalent to ABTI cyclic. So we know that ABT is just angle B. We know AIF is 180 minus AIC, which is 90 minus B by 2.
Your voice is breaking again.
AIT is equal to 180 minus B. And that is better now. Is it better now?
yes.
Okay. Okay, so yeah, we got AITB cyclic because AIT is 180 minus B. And so we're done. So I'll just go over the last part once more. We wanted to prove TIMS B, which is equivalent to AITB cyclic. And we found AIC, so we can find AIF, and that's just half of AIT, so we can find AIT, and that turns out to be 180 minus B. So we can show that AITB cyclic, therefore this angle is B. So I hope that much was clear. If anyone has questions about any of the steps, then please ask. So for this, we needed AITB cyclic. Okay, so if nobody has any questions, I'll move to the next problem.
Yeah.
Okay, so you have again circumcircle of ABC. You have a tangent line. So you're given some points D and E on AB and AC, such that BD by DA is AE by AC. So it's a slightly strange length condition. And you're given lines through D and E parallel to the sides, which intersect the tangents at H and I. And you want to prove two things. You want to prove that FGH I are cyclic, and you want to prove its tangent BC.
Your voice
So
is breaking.
Okay, so your voice is breaking a bit, like quite a lot.
any observations you get is done. Can you
It's still breaking quite a bit. Sorry. Please continue. There was some misunderstanding.
Yeah, this one. Yeah, so by angle tracing, we can, so because of the tangency, we get this angle to be C. And this is also C because of the parallel line. So we get these two quadrilaterals to be cyclic. And also, okay, since we want to prove FGHI tangent to line BC, it would be nice to find the point of tangency and then maybe just prove that that point lies on the circle. So is there any point that you think could be the point of tangency? Or maybe some claim that you think could be true in this?
Midpoint or
The
something.
angle bisector.
Midpoint of BC seems tempting because of all the parallel lines.
That could be true. Also, is there anything else you can do with the parallel lines? Like maybe introduce some point on BC that makes the ratios nicer, especially since you actually already have these parallel lines. So if you looked at these 2 points, what would that give you?
I'm sorry, which 2 points?
The intersections of these 2 lines with BC, you can call them X and Y. You already have some ratios and you have the parallel lines.
What do
So
you know about the relation between F and H? I mean F and G.
F
Can we
and
state?
G.
Yes.
Perhaps the ratio of the ratio.
Oh wait, I think X is equal to Y. Like
yeah.
X and Y are the same point.
Yeah.
Yes,
was-
because
Yeah.
you have BD by DA is equal to BX by XC, but this is also equal to CE by AE by AC. And this is equal to CY by, no, this is equal to BY by CY.
I don't get. Isn't it just because we have a parallelogram? A F X E is parallelogram. That's why.
Sure, but we don't know that those 2 points are the same yet. So we're trying to show that the intersection lies on BC. So we get these two ratios. So if we assume they're distinct, we get bx by xc is equal to by cy. But that can only be true for one point on BC. Like that ratio can be true. That's why x must be equal to y. I hope that's clear. Now
Wait,
I'll
but
just make.
can you show that both those points are not conjugates of each other?
No, because the ratio bx by xc. So this ratio, it can never be the same for 2 points on the segment.
Because they're both inside the segment.
Yeah.
Well, how do we show they're both inside?
Because like you're drawing a parallel from a point in the segment. So like the directed ratio BPT works if you want it that way.
Yeah,
BPT? What is BPT?
This is basic proportionality theorem.
Oh, that.
Yeah, okay. So this is a single point. Let's just call it x. And okay, now we know that AD
is the parallelogram.
Yes, yes.
Right. So we can get some similar triangles such as BDK, BDX and BAC, CEK and CAB. So basically, since BDX is similar to BAC and CEX is similar to CAB, we can say that all three triangles are similar, and that gives us the parallelogram ADKE.
Alternatively, you just have ADKE, right? Yeah. So you just alternatively you just have that AD is parallel to EX and A is parallel to DX.
Right, and we get those three similar triangles, and then we can actually have similar triangles ADE and IEG, if I'm not wrong.
Wait, which three are similar again?
DBX and ABC and EXC.
Okay.
Yeah. Okay, so we have, I think you were saying these triangles as well. Doing this.
Right, these triangles also.
Yes. So now can you see anything that is related to what you want to prove? Maybe using these angles.
So we just show that H, I, G, X, F are all. So if we show H, F, X, I are concyclic, then we're done. Because by symmetry, the other one also will hold.
That is true. And can you prove that if that circle existed, it is tangent to BC?
And HIX
Yeah,
is
that's just trivial because HXB is HIX.
Yes. Okay. So now you just want to prove that F and G lie on HIX.
I'm sorry, what does it reduce to prove?
That F and G lie on HIX because we showed that HIX is tangent to BC.
Is this step equivalent or is it wishful thinking?
Okay, you can think of it this way. You want a circle passing through H and I tangent to BC. And you just
Okay,
showed,
right. Fair.
yeah, you showed it's passing through X.
Isn't it like also equivalent to proving that triangle ADE is similar to triangle?
How do we know if it exists, it's tangent to BC?
We just, so you know that there must be a circle passing through HI tangent to BC.
No, like HX is already tangent because HXB is equal to HI.
Sure, you just prove that HIX is tangent to BC. And that
How do you do
must
that?
be the unique circle.
How do we show
Because
HXI is valid?
IXC is equal to B.
Ah, yes, got it. Got it.
Yeah, that's what I'm saying. IXC is
Your
equal
voice is breaking
to
again.
B and IHX is equal to B. Yeah, so I just want to show F and G lie on that.
So then I want to show that basically FG is the radax is one thing.
Yes, that is true. And
F.
how could you show that?
So we show power of D
Okay,
and
yeah,
D
so if you show that
equal
F,
both circles. So dA into dB should be equals
exactly,
dH into dx
yes.
and E also.
And that's true. So we're done.
I didn't get it. What did you say? How do we
Okay,
show
so
So we
radical
want
what
axis?
we're
to show
doing
that,
is we start by showing that, okay,
go
so
on.
first of all, we want that FG to be the radical axis of the circles HIX and ABC. That
Yes.
finishes because then FG is the common chord, right?
Yes, yes.
So since FG is basically DE, it suffices to show that D and E have equal power in both of the circles.
Yes, yes.
Now the power of D in ABC is AD times DB. And the power of D in HIX is HD times DX. But we've already proven by angle chasing that HAXB is
They're just
cyclic.
similar triangles.
So we're done because then both of those powers are equal.
Yeah, because similar triangles. Got it. Yes. Yes. That's nice. That's neat. That is very neat.
Okay, so I hope
Your voice is breaking a lot.
yeah, this is the problem was to first realize that X lies on BC, which you can prove using ratios. He showed HX tangent to BC, G lie on the circle.
Your voice is not clear.
I mean, she's basically just saying that
Is it
the
audible
first.
now?
Okay, fine. Yeah, you're audible.
Okay. Yeah, so we wanted to show that F and G lie on the circle, and you already know that they lie on AB. So if you show that they lie on the products of ABC and HX, that would mean that that is the common chord. And we just show that by POP on D and E. Okay, so we'll do one more problem. So the last problem I have is this, and it should not take very long. So you have ABC as a triangle. So there's a common configuration called Simpson line. So I just wanted to make sure that everyone's familiar with it. So I'll prove that first. It just says that if you have a triangle ABC and a point P on the circumference, if you drop perpendiculars from P to all the sides.
What just happened?
He's left. I
Okay.
think she got logged out. Let's wait for her to be back.
Did anybody take a snipping tool of the question?
No.
No, but Sanjana is back.
Can you hear now?
quickly take us?
Yes.
Yes.
Yep.
Can you?
Yeah, okay, sorry about that. Yeah, so Simpson line just says that these 3 points are collinear. And yeah, if someone wants to give a quick proof, you can do that, else I can give the proof.
Angle chasing should work, right?
angle chasing works.
Because if I use directed angles, then we have PYZ equal to PCZ equals PCB equals this PAB, which equals PAX, which equals PYX. So we're done.
Wait, could you repeat that? What did you start with?
So we're using directed angles first of all. We have PYZ equals PCZ, which equals
How is
PCB
PY? How
Wait, that's
how is
90.
PYZ
Yeah.
equal to PCD?
This is
because
90.
directed angles. So cyclic just means that the directed angles are equal. Like, yes, the angles are 180 minus each other in this case, but directed wise they're equal. So
Yeah, okay. So
so
PYZ
PYZ equals PCZ equals PCB equals PX, PAB equals PAX, I think, yeah, equals PYX. So we're done.
PAB
First, can we just
equals. What does PAB equal?
PAX,
Okay.
and then
Yeah.
that's equal to
So
PYX.
yeah, this is basically the angle chase. So I hope this is clear. It just says that you have 4 cyclic points. You draw perpendiculars from one of them onto the other 3 line segments, and they're linear. And it's just this angle chase.
Yeah. Simpson's line and then next one.
Yeah, it's called Simpson's line. So now let's try this problem.
I mean, it reminds me of some APMO, but I'm not sure.
I mean, it's used in like 2010 USAMO1 if you
so
want
what
to use it.
so what is the Simpson line definition again?
The line formed by those 3 feet is a
Basically, like
Simpson line
the
of the
point on the circumcircle of ABC, that is extended to form feet of perpendiculars on the sides, lines, and the feet of perpendiculars there are collinear.
Oh, that's nice. How did you do that?
The angle chase which I just said works.
Yeah, angle chasing.
So you did that PZ PYC is equal to PZC.
Sorry?
How did you start?
No, like first of
PCZ.
all, like you try to prove that the 3 points, the angle between them is 180 degrees. Like that is a good angle. You know? Like
Okay, so you want to
You
prove
try to
it.
prove first of all that PYZ plus YX is 180, or in directed angles PYZ equals
yeah.
PYX.
Okay, what if they're just 360 degrees away? Won't
Yeah,
that
exactly.
happen?
That's why we're using directed angles to avoid that.
If you want, I can show the proof again without using directed angles.
Yes, that would be very nice.
Okay, sure. Okay. So what you have is, yeah, you have this angle is equal to 180 minus this angle, right?
Yes.
And you have that is equal to this angle, PAX, because APBC is cyclic. Is that fine?
Yes.
So now you have that is equal to PYX, but you already know that these angles are 180 minus each other. So
So you're done.
XYZ is equal. Yes. Okay. So now we have this problem. So you're given that M is the midpoint of BC and N is where the angle bisector intersects BC. And you're taking the perpendicular at N to AN, and it intersects AM at Q and AB at P. And the perpendicular to AP at P intersects the angle bisector at O. and you want to show QO is perpendicular to BC. But if you call this point L, you know ML is perpendicular to BC. So you can also show QO parallel to ML. So I hope this statement is clear. And yeah, any progress you get, you can tell.
I'm just confirming the line L you constructed as the midpoint of arc BC, right?
Yes, it is.
So like homothety, because
Sure, yeah. So all you need to do is show that there's a homothety sending O to L and Q to M.
How did we use homothety?
So you have a homothety at a point that sends this point to this point and this point to this point. You know that these are parallel, right?
Okay.
Yeah, that's all you need.
so Mira, homothety is showing that Q goes to which point?
Q goes to M and O goes to L. That would show that
Q does not go to M. The point of intersection of OQ and BC goes to M, right?
no, okay, you want to show QO parallel to ML. So
Yeah.
it supposes to show
So
Q
then
goes.
QO cap BC should go to M if we're considering homothety. Because collinear, right?
We are considering about
But
A.
we're considering a homothety about A.
Oh, okay, then no.
One thing you could note is you have an angle bisector and you have a 90-degree over here at N.
Yeah, so
So
maybe make PN intersect AC as some R.
P square equals AN into AO because of similar triangles.
yes, that is true. So what can you say about R? Because
So
everything is
LR is
facing.
perpendicular to AC.
OR
Wait.
is perpendicular to AC.
Sorry, yeah.
Yeah, sure. Okay. And this is just because of similar triangles, or you can just say you're just reflecting about the angle bisector. So
And I
OR is
guess that,
perpendicular.
and then OPAR is cyclic, right?
OPAR is cyclic, yes.
And then of APR.
Did you say something after OPAR cyclic?
No, cause like that's a simple line of APR, right?
Simpson line of APR. Yeah. So if you consider APOR, then I guess PNR is the Simpson line when you have perpendiculars.
But then like PNR is just like the side, so
Yeah,
that's
that's
We can drop
so,
perpendiculars from L to AB and AC, and we are done, or are we?
yeah, I think we should be done because
Yeah, wait.
this
It's
is
similar,
yeah.
so and it's perpendicular, like the foot of those perpendiculars like pass through M. So yeah.
Yeah. Yeah, so you have this line, and when you drop the perpendiculars from L, you get a line which is parallel because L and O are both on the angle bisectors. So that
Wait,
would mean
how can you say it passes through O? Does it not pass
it does not pass through O. It passes through these
M?
2 points.
It passes through M also, right?
Yes.
Yeah.
So that means you have a homothety sending this L1 to L2. Right?
So Q goes to M.
And O goes to L, so we are done. Nice.
Wait, so then wouldn't N go to the point on L2? So we're not actually done. We can't say about O yet.
Yeah. No, okay. Consider these 2 triangles, POR and XLY. So you know POR goes to XL.
Ah, okay, yes, that's also.
So O goes to
Yeah,
L, and you know that Q goes to M. Yeah. So I hope it was clear.
Wait,
So
why
what?
does Q go to N?
Because we know L1 goes to L2. So you just take the right through A. Q must go to M.
Oh, okay. Yeah, makes sense.
Okay. So I think the main idea of the problem was dropping the perpendiculars from L to sort of get a homotopy. And then you realize it's the Simpson line config. And then you're basically done. So yeah, those were the problems I had for today. And yeah.
Sources?
I can send the sources after the
Okay,
class
sure.
and compile them. And yeah, you feel free to like ask for hints on the extra problems or send me your solutions if you get those. Yeah, I hope you like the class. I'm sorry about the internet issues.
Sorry, but send it where?
If you want, you can send it in DM.
Sure, thanks.
Okay, sure. Yeah, thank you for it.
Bye, thanks a lot. Thanks for
Thank you
teaching.
so much.
Thanks for the
Thank
class.
you. Bye.
Thanks.
Thank you.
Thanks.
Yeah.